Ladies and gentlemen, welcome to the Ryan Ride Mechanic channel. How the heck are you doing today? Alright, today's video I want to talk about how a Funtime Starflyer works. Let's get into it.
Now get ready, here we go.
Okay, so today's video is the Funtime Starflyer, and we're going to talk about how that works. So if this is your first time here, what took you so long? Honestly, come on. Get with things. I've been doing this for a while now. You need to reach out and branch out through YouTube more. Now, if this is your first time here, make sure you like, subscribe, do all that stuff, turn on notifications so you can see when my videos come out. I try to put them out once a week on Fridays, and I typically release them at 11 a.m. Central Standard Time, in case anyone's wondering about that. All right, the Funtime manufacturer put out a ride called a Starflyer. This ride had immense popularity back in around the 2010 era, somewhere around there. Six Flags started buying them up like crazy. They started putting them like almost one in every single park. The size of these rides varied. My particular park, we got one in that was 150 foot because that was the size that we got. Now, one of the fun things about this is when Funtime came to the park to install it, it was like a 150-foot model, and they said, yeah, we've already put some in around that are 400 feet high. It's like, wow, that's pretty amazing. And they said, yeah, your model, that we didn't even know we could make one that small. We were joking around. It's like, oh, what'd you do? You just took the base and the top and kind of put the two together with no middle sections. And hey, it's 150 feet. Yay, there you go. All right, let's start in with the operation of the ride. The ride sits down in the home position, load position. All the people come in, they sit down. It's typically in seats, and I'll go over this stuff a little bit more in detail in just a little bit, but typically you sit in a pair of seats, or two seats right next to each other, suspended by chains, and then they hit the ride cycle start. It lifts the gondola or the star up a little bit, and then it starts to spin. Now from here, every ride at every park kind of varies on what happens between each other. So some might spin really fast at the bottom and then go all the way up the tower and then spin fast up there and then come back down and stop. Some might go up and down and up and down. Some might speed up, some might slow down. There's all sorts of things that parks can do to these things that doesn't necessarily have to have the manufacturer come out every time. So there was programs that the park can select. Our particular model, we had 9 programs in there. Now, 2 of those programs were actually maintenance programs. The maintenance programs we used for testing things because we had to get the ride in this certain type of function, and then we were able to test certain speed tests and overspeed, over height, and things like that. But we had to be in those special programs which require maintenance keys to be in them. Okay, so after the ride cycle would stop, it would come back down to its what's called park position. That's where all the swings stop about 15 to 20 feet off the ground, and then it comes back down, lowers down to the load position where it's pretty much your feet are on the ground, and then all the restraints unlock, everyone gets off, people come in, start the next cycle up again. That's an average cycle for those rides. Again, depending on the park it's installed in and what they wanted to do, the actual operation of it varies drastically. So I don't want to get too hung up on like a cycle, because my cycle is different from any other park cycle, and then we can get even more different just in my park by itself. We had all sorts of other cycles we could run as well. Okay, so let's start with the tower construction. The center of the ride, what everything sits on, is typically referred to as a tower. On some models, like my particular model, the tower was constructed of box and tubular steel, bolted connections, and each one had a like crossbar. It was basically like a zigzag all the way up each side. And then there was a top. In our case, we had a globe up there, big ball covering, but that's where just some pulley sheaves and other things were up at the top. Not too much there. At the very bottom of ours was where our lifting package or our winch package was located. Now in the earlier models, they actually put them up at the very top of the ride. That's where the winch package was. But the models that came later on, they started all putting them on the ground, which, oh, Thank you so much for putting them on the ground. I can't tell you how much I appreciate that. Oh man, to fly up that tower each time, anytime there was a fault with a motor, would have been absolutely ridiculous. On the bigger models, the ones that were like the 300, 400 foot models, those guys were made up of pretty much flat plate constructions that were bolted together as well on theirs. Not so much tube, but more of like plate steel and angle iron bars, stuff like that as they went up. It made for a much stronger structure in there where the tower was really allowed to flex and move more. Now the tower had 6 sides to it, and on each one of the 6 sides there was a pretty much vertical runner, whether it was out of flat bar steel or whether it was out of just tubular steel. The flat runners on each one of those 6 sides is where the star guide wheels essentially ran up and down the tower. Now, when you're installing a tower this size, you would think like, well, what goes into that? What is holding that tower up? And there is a giant metal framework. Unfortunately, I don't have any pictures or anything like that of it, but there is a huge metal frame that's buried in the concrete in the ground. It goes down really deep, and it gets very wide.
That's what she said!
Out there. It's like the entire circumference of the ride down there, man, it has to be 150 feet across, is all a metal substructure in the ground. It's very big, and that's what keeps the ride vertical. Now, part of the NDT to these rides is every year you have to go out with a survey company and survey the tower itself and the ground and certain markers around it. So there's dedicated survey markings around the ground, and they go out and they shoot the tower. By shoot, I mean they survey the tower, and they make sure that it's still standing perfectly straight up and down within I think it was like half of a degree, had to be standing perfectly straight up and down. And then the ground had to be shot into level to make sure the ground wasn't sinking one way or another. So the actual NDT for the ride was simply to resurvey it and make sure that nothing was moving. I don't know what we would have done if something was moving. I mean, you can't just jack up one side and correct it. I think if something was moving, you'd pretty much have to take the entire ride down and tear that base out and redo it and re-pour all the concrete. Probably would have been the end of the ride if something like that were to happen. All right, from there, let's move on to the star. Now, the star is the piece that rides up and down the tower. In the very center of it, it's made up of 2 components. There's an inner ring that hugs the tower, and this is where the guide wheels are on all 6 sides that guide it so it stays perfectly centered around the tire. That center ring has the outer star on it, and the star extends out with these extension arms that holds the chains where your seat's attached to. Now, the reason why they're 2 separate pieces is because the star rotates 360 degrees around while it's going up and down. So to do that, they have that center ring that sits there, and it actually has a bunch of basically vertical wheels all along the bottom of it. And then the star sits on top of that, and it's got a bunch of horizontal guide wheels that keep the star rolling in the center. Now, in between those guide wheels that keep the star rolling in the center, in between those guide wheels and stuff on the star, there was drive motors in between the guide wheels on the star. And the drive motors are spring-loaded. They're just rubber tires. They're like booster wheels you would find on a roller coaster. It's just a vertical SEW gear motor with a rubber booster wheel that's pushed up against the inside of that ring of the star. And then as those booster wheels turned on and started being powered, that would start to drive the rotation of that star. Now, the booster wheels were on the center ring because they had a cable that stretched down on both sides. One cable was for power, the other cable was for communication. So as you look at these rides as they go up and down, you'll see kind of these long wires going all the way down, in our case, to the bottom. At the bottom of the ride, there's these giant spool collectors which have counterweights on the bottom of it. Those are cable tensioners. All that is electrical. So basically, as the star goes up, the cable electrical goes up with it. As it comes back down, it retracts back down and goes back onto those big reels. Now, one side is high voltage, the other side is low voltage. The high voltage side has all the stuff for the motors. It's mainly like it's a 220. I don't think those went higher than 220, 208 on the feeds for that three-phase motors. They might have had 480 in there actually. I honestly can't remember if those feeder motors are 480 or 208. I want to say they were 480 because that one side had to be completely separated. The other side was communication back to the bottom. So the communication process from the star back to the bottom, there was a lot of stuff on that star and a lot of things to watch for. So like I said, you had the drive motors which turn the star around. Well, anytime you have anything rotating, you care a lot about the speed. So on the drive motors, you had all sorts of encoders. For these encoders, they used a module called the MSR module that was watching each one of the drive motors and feeding its information back to the controller. There was actually two controllers. One was on the star, one was on the center. The center would handle all the stuff like the drive motors spinning around. The star handled the communication out to the seats. The seats are like nothing else. They are safetied out to no end. So there was a lot of communication happening right there. Now, to get the communication from the rotating part of the star to the solid part of the star, there was a giant set of slip rings that went all the way around the ride. It had a trolley stuck up on the inside, and the outside of the slip ring was communicated to the center stationary base. That's the part that would ride up and down. And then the trolley was on the rotational part of the star, and that would take the signal around from there. Now, originally, our ride had a bunch of communication and all sorts of other stuff going through that slip ring. I believe it was a 8-conductor slip ring. So that means on the inside there could have been a total of 8 wires touching that collector. And then when we were done with it, we were only using 4 of them. 2 for power, 2 for communication. Wasn't much to it. But we didn't start there. That was a long road to get to that spot. So as we work our way out from that center, like I said, we've got the processor, which handles all the logic. That's for the seats. And then further out, there's not much. It's just a bunch of lattice work, very much triangular, that goes out to a point. And then that's where the seat chains mount in between the points of the stars like that. The seat chains are very interesting. We really wanted to know, we as in like the mechanics that were working on the ride, we really wanted to know how heavy duty those seat chains were, because when we first got those things, we were looking at those seat chains and we were like, what is this? And they're like, that's the seat chains. Well, how many of them are there? Well, actually, as I'm sitting in a seat, there would be 2 chains off the front, 2 chains off the back. The seat pairs are welded together. It's a solid weldment. And then the other seat next to me would have the exact same things again. So I'd have 1, 2, 3, 4. There was a total of 8 chains. Our only problem was the chains were like something you would see on like one of those bikers' wallets where it had the chain coming off the wallet, hooking it to the pants. That was the size chain that held those seats on. And we were really curious as to how long those chains were going to last, because it looked like it was way underkill. We had a Zamperla flying carousel on the midway, and it had chains that were like 6 times that size, holding just one little tiny swing on. And then we're looking here at this thing going up 150 feet and extra G-force on it from high rotation and everything, and we're just like, really? Those chains are it, huh? That's all you're going to have? Ooh. We didn't like that, but the manufacturer stood behind it, Funtime stood behind it, or engineering stood behind it, so it was like, okay, those are the chains that we're going to use. All right, the chains as they went up, the chains went up on top to a spreader bar. The spreader bar was there in order to keep the chains vertical down to the seats. That's so the chains didn't try to steeple above your head like this. So they went up vertically to that spreader bar, and there was a bar stretched across them. And then from that spreader bar, then they went up at an angle and attached to a single point that was between the points of the stars. And ours had 16 swings going all the way around it, 16 sets of swings, which would be 32 people riding on the star at one point in time. Now, for the seat itself, we had these Allen Bradley Guard Logix things that was really complicated. That was like way more complicated than it ever had to be. And I say that because I asked. I asked how complicated this is. Because what we started getting was like every time, okay, so there's two seat belts, one that goes across your lap, one that goes across your chest. Where they would plug in, the one that plugs in up here across your chest, and the one that plugs in down the lap, it went into an Allen Bradley Guard Logic safety modules. I've had pictures of these things before on the channel. These things are like 4 channels monitoring, safety rated. They lock in place. You can only unlock them with a safety signal that comes from a safety processor, like all this stuff. We had so much troubles with these things. It was unbelievable. We had the heads. What happened with guests would, as they would pull the seatbelt buckle out, it looks like a Pac-Man where they would lock into the seatbelt buckle. The Pac-Man would eventually just let the seatbelt buckle out, and then with nothing inside of it, it would roll back over and lock again to where the next time you put the seatbelt buckle in, it wouldn't do that. Now, I've had this on some stories before, so some of you might remember this, but what we did is we contacted Allen Bradley and we said the little heads are wearing out. And they said, what do you mean? And they're wearing out because as we could pull these little tongues out of there really quick, the mechanism locks back on its own. And they said, well, that's impossible. That can't lock back on its own. That thing can't lock on its own. It's safety rated. It won't do that. As soon as you pull that thing out, it opens up, nothing else. So we sent them a bunch of pictures and videos because some mechanics were able to do it. Just like, whoa, yep, oh, look, it won't go back in there. So we said, all we need on that little module, all we need is just the head.
That's what she said.
Right? We just need that little head module, that Pac-Man that goes in there. But because they were safety rated, they would not sell us just the head module. We had to buy the entire thing over again. This was back in I left the park in 2018. But I mean, this was pretty much from like 2010 on. Those things were like, I want to say they were like $500 or $600 for one. So if you think about it, $600, $600, $1,200, $2,400 in a pair of seats. It's like, that's a lot of money sitting there. So when we were having all this trouble with this, I asked Funtime because when the ride was brand new, we had guys that would stay there and they would make sure that they were handing over the training, they were watching the equipment, they were staying on top of any adjustments and letting the home office know if we had any troubles with stuff. So I said, with all these pain in the butts that we're having with all this stuff and the processors will lose communication to them and stuff like that, a lot of trouble. I'm like, what do you guys do on your other rides? And they said, we don't have these on our other rides. What do you mean? They said, your company said they wanted to put these on this ride. And I'm like, so you don't use this style on your other rides? And they said, no, we don't use these at all on anything. So I asked, oh, what do you use on your other rides? And they said, it's pretty much just a spring-loaded clip down there at the bottom, just like any swing ride. Just a mechanical spring-loaded clip that just goes right on the bottom of your seat. I was like, really? What? You could unplug that. Like you could just open that mid-cycle. And there's, yeah, you could. I'm like, well, what happens if somebody does that and falls off the ride? Well, that's their problem. That's not our problem. I was just like, wow. I said, here in the U.S., you would get sued like to no extent. You'd just be sued left and right, like if you were to do something like that. And they basically said, I can't remember the exact verbiage they used. It's translated. English was not their first language, but it was translated, and it is basically like, yeah, in another country, if you did that, the park would come after the family that did that for damages done to their equipment. And that was another one of those things. It was just like, wow. In a country run by lawyers, this is what we have to do to survive. It's just like, okay, but those are the seats. So I covered the seats, the base, which is just metal frames with just a plastic bucket seat sitting in it. These massively overcomplicated Allen Bradley Guard Logics controllers that operated the seat belt itself, and the seat belts locked. Once they came out, they locked in place. And then the chains that went up to the spreader bars up to the top and connected back to the star again. Now, remember I was talking about the slip ring pickup in the Star. I said where there was 8 conductors and then we got it down to 4 conductors. Because what happened is a lot of that communication went through that slip ring setup and then back down to the bottom. Well, we had so much trouble communicating from the Star back to the control room. We had so much trouble communicating with that.
I don't know what all this trouble is about, but I'm sure it must be your fault.
That we eventually gutted the system and we stopped trying to communicate over wires and we started using wireless signals, like a Wi-Fi signal essentially.
That isn't very reassuring.
So we would run power to the Star and we would run 2 wires of power, it was basically 115 volts, like wall voltage. We'd run power up to the Star and power the Star up with that, and that would power up its MSRs, its encoders, it would power up all that stuff. And then this was also enough signal to power some other power supplies where once you hit the unlock button, it unlocked the restraints, which was nothing big for that power. It's like it only ran off of, I think, 10 amps at the most, but never really used any of it. Kind of just like a wall outlet at your house. And then we ran the communication part through a wireless signal. And then once we went to wireless and found the right channel, because we also found out that all the Dippin' Dots carts around communicated on the same channel and also threw off all of our Wi-Fi setups as well. Once we found the right channel to communicate on that was quiet, that the rest of the park wasn't using, the machine started working great and we started dropping all those communication faults and it relatively worked good from there. So that is the Star, rotation, all that stuff. Alright, so how do you get that Star up and down the tower? Well, we're going to use a set of cables, lifting cables, steel cables, 16 millimeters in diameter, a steel cable that is doing the lifting. In this case, steel cables are called wire ropes. So we used wire ropes to lift the Star up and down. Now, we didn't just use one wire rope. We have to think about redundancy. So we used 2 wire ropes. Actually, we didn't use 2, we used 4. Actually, we didn't use 4, we used 6 of them. 6 of them. Wire ropes to lift the Star up. And the key thing is every time the Star made a corner and bent, so all the way around that center tower, in every corner, that is where we lifted the Star up. Those cables went straight up to the top. There was 2 collectors along the way, or cable spacers. These are basically just guides that sit on the outside edge of the tower. I've got a close-up video of one of these from Superman at Magic Mountain. Not Superman, but Drop of Doom on the side. As the gondola is going up, it passes these cable collectors on the side of the tower, and the gondola picks up the cable collector and comes with it. And the reason for that is that once you have a long stretch of cable going down the side of a tower, and the thing's only spaced off about like 6 to 8 inches, somewhere in that area right there, anytime you get wind and stuff like that, those cables tend to slap. They'll slap the tower, they make noise, plus every time you slap something, it's an impact on the cable, and you shouldn't be impacting those cables. I say cable, I do it all the time, but again, the official term is a wire rope. I apologize, I'm going to say cable a lot because that's what I'm used to. Official term is a wire rope. So those wire ropes, cables going up there, they pass through collectors that basically just space the cables apart from each other so they don't go left and right, and they also space them off the tower so they don't go in and out. And then as the Star come up, those spacers around the outside essentially just lift up off of their little stand where they're on. They just stay with the Star as they go up. And then the second picks up the second one as it goes up, and then when it comes back down, those little spacers simply just have 2 little dimples they sit on each corner. And then as it comes back down, it just hits the dimples and then falls down with the rest of it. So the 2 pieces separate essentially. So as you're coming back down, you're coming down past the 66% mark. The first separator stops and the Star continues to go down. And then once you pass that 33% mark, the second separator stops and the Star continues to go down. So those are the separators keeping the cables from slapping the side of the tower. On the top of the ride, we had a globe on top of there. It made it look really nice, but realistically inside that globe is a ton of pulleys and sheaves inside there. So each cable went up the tower. It had to turn 90 degrees and go over another pulley and then come back down. Now, when they came down, they all went past one standardized point. So all these different 6 cables coming in from different angles, they all suddenly lined up and were now in a nice straight row. Now 6 cables across, and they all went straight down. And the deal was they went straight down all the way to the bottom, and then they went over the winch package, which is a drive motor at the bottom. Big steel drum, so they went over that big drum, and then they came all the way back, all 6 still in a straight line, all the way back up to the top, and then they went over another drum that wasn't driven, it was just an idler, but they went over another drum and then came back down, depending on where the star was, and they met up with a large counterweight that was in a track. So you had the drive motor lifting and lowering the star, and then you had the counterweight on the other side. So as the star went down, the counterweight went up. So if you're looking at one of these rides while it's down in the load position, you can see the counterweight all the way at the top. It looks like a big, kind of hard to describe, it looks like a giant door that's sitting in the middle of the structure. It just looks like a big rectangular chunk sitting there. And then as the star goes all the way up, if you've ever been waiting in line for one of these, you might notice that once the star is all the way up at the top, you'll see this thing that looks like a big metal door come down all the way to the bottom and pretty much just stop at the bottom. And it just sits there. And then after a little bit, it starts to go back up again. That is the counterweight. It has come all the way to the bottom because the star is all the way at the top. So it is just sitting there while the people are up at the top spinning. And then once the people start to come back down, that counterweight starts to lift back up, and there it goes. The counterweight on these systems is necessary to provide the tension on the main cable drum. So once the cable goes through that drum, if you take the counterweight off the one side, the star is really heavy, there's not going to be enough tension on those cables for that drum to efficiently drive it, and it might slip. Now, what's interesting about this is that the drum, or the counterweight in this case, is actually heavier than the star is when it's unloaded. So actually when the star is at the very bottom and everyone gets off of it, that is the worst possible condition because you have the full counterweight up at the top, which is meant to offset a full star worth of people. And then when everyone gets off, that star is unloaded. So when it's in the load position, the star can actually fall up. It's a weird one to think about, but the star can actually fall up if it were to somehow lose tension across that drum. There's still plenty of tension on there. It's not going to go anywhere, but it's kind of weird to think about. Oh yeah, this star would fall up. That's a weird thing. Truly is. Now, those are the 6 lifting and lowering cables that are going over that big drive drum assembly. Now, there's one more cable that's attached to the star. It's going up. It's very small. It's only about 1/8 inch in diameter. It's going up all the way back over the top, back down, and it grabs the star on both sides. So as it goes up, it automatically just reels up and back down. So it's a closed circuit cable on itself. That one is going to a funny shaped little square wheel down in the control room or the winch room downstairs. That little funny shaped wheel is the speed governor for the ride. Now, what that's doing is that's operating an old-fashioned, by that I just mean the technology's been around for a while, nothing groundbreaking in this ride. That's operating what's called the fall brake. On the tower, you've got the 6 sides, there is 2 elevator rails, 180 degrees apart from each other, and on those rails in the star, in the stationary part of the star, rides the fall brake assembly. Now, what a fall brake is on an elevator. Have you ever been on an elevator and worried like, oh man, if the cable was to snap, the elevator would just fall? Well, there's a device on there that prevents the elevator from falling in that scenario, and they're called fall brakes. The fall brake is essentially 2 wedges that are on the inside, sloped like this. I'll make a diagram so it looks nice, basically. So these two wedges sit open, and that vertical fin of those elevator rails pass right through the center of that fall brake. And then if it were to go down with any sort of speed whatsoever, the fall brake mechanism down at the bottom of the control room stops that cable, and then the cable pulls up both the wedges at the same time and basically wedges them against that center fin, locking the entire assembly. That fall brake is tested weekly. It works great. That thing isn't going anywhere. You can literally blow apart all 6 cables, and that star would fall only about 1.5 feet before those things dropped in, and then it's stuck. And it's like once it's there, you can't get it unstuck until you lift the entire star back off of them. And most of the time, even once it's back up a little bit, you have to take something like a punch and a hammer and drive the wedges back apart for them to actually open up, and then the star can come back down the rest of the way. Now, I know a lot of people are just saying, well, what happens if that speed governor messes up and it never grabs the cable? Well, that's one of the interesting things about speed governor. It is electronically controlled. So when the ride says, I'm going too fast, it will automatically stop the solenoid, grab those cables, and then it will stop the assembly. It's automatically controlled. I understand there's some air there, but at the same time, it's got a clutch on the inside of it as well, to where when the cable just starts going fast, kill the power, right? No power at all. When the cable just starts going fast, that clutch automatically just puts enough drag on the assembly to where it wants those cables to bite, pulls those wedges in, stops the whole assembly. So the thing's really fail-safe. It's really good. But that fall brake is a very important part of the assemblies. Down on the winch package down below, it is a giant AC motor with a very large gearbox and drum assembly where all 6 cables go across it. And then on the outside of that drum assembly, there is let's my measurements right, there is a 3-meter diameter disc brake. Right? It is massive. There is a 3-meter diameter disc brake on the side of that drum. And then on that disc brake, there is 2 calipers. Just like you think about your brake rotor and calipers on your car, it's the exact same thing, except for these calipers need hydraulic pressure to pull them away from the rotor. And then as soon as you hit an e-stop fault, anything like that, the solenoids drop out, all that hydraulic pressure leaves, and it instantly closes and grabs a hold of that disc. Now, when we were commissioning the ride, they spent a lot of time making sure that once those calipers opened up on a daily, that we needed to check to make sure the air gap was exact on both sides. Only about 1 millimeter is all they wanted in there, 1 on each side. But they said you can never have it to where one side of the caliper has 2 millimeters and the other side of the caliper has none, because unlike your car, these calipers don't float, which means your floating calipers on your car will always find center wherever your brake rotor is. These calipers do not float. They are mounted solid, so as soon as those things push in, if it's too far off to one side, you could literally shatter the rotor on that assembly. And they're like, you don't want to do that. That's a long lead time part. You would have to take the whole ride apart to replace the thing. So they're like, always ensure it's the same exact distance on both sides of the rotor. Never 2 millimeters and 1 millimeter or something else like that. So it's like, okay, took that away. Now talking about the winch package, this is a good time to bring up emergency recovery, because this is a very unusual creature. It's got lots of little things to it. The star is heavier than the counterweight. Unless there's not enough people on it, then the counterweight is heavier than the star. You've got a hydraulic brake caliper that's essentially shut, and you have to have power to open it. All these things. So let's talk about some of the things that have to happen in order to move this ride. In maintenance mode, it's really simple. You put your keys in, you reset everything. When you hit reset, that main caliper opens up, and then you can manually on the touch screen just move the star up and down. Not a big deal. If you can't get that to happen and the control system is dead for some reason, like it's not responding, you're in a world of trouble, and you need a lot of people to manipulate this ride, because you have multiple scenarios happen on. Let's go with the easy one first. The easy one is that it was a fully packed day and the star is fully loaded with heavy people. So you don't have to worry about it. They're at the very top. It's like, okay, how do you get those people down? You have to manually open both of the brakes on the ride. Now, I talked about the big hydraulic brake that was sitting there. That's the main one. There's also a secondary one that's on the actual AC motor on the end. It is just the regular motor brake, but it is still one of those things where you have to push a rod into it and hold the rod open. Then you need another person to manually override the hydraulic cylinders, the two little solenoid valves, which they give you a nice little handle. And then there's a pump, and you essentially pump the hydraulic pressure up until those guys open. Now, this is your best case scenario. Everything's heavy up top, so you're on radio communications, people are watching.
Well, we're waiting.
Operations is ready. They said, yep, go ahead and move it, and you pump those two things open, and you open up those two brakes, and the star starts to just come back down. It's like, okay. It doesn't go fast. There's enough drag in the entire assembly to where it doesn't go fast. It will just naturally come down on its own. And then as soon as the people are down, right about to the point where you look out and you could say, yep, people are going to touch their feet on the ground, that's when you let everything go. And then you go out, and at this point, you go to the seats. There is a manual unlock underneath the seat. Because the thing is safety rated, remember those safety rated modules I was talking about, it's not easy. It's not like flipping a lever, although there are models where they actually do have a lever on the front. They didn't put those on this ride. These are actually, you have to remove a safety screw, and then once you take that screw out, you have to put another tool on the inside to push open the lock manually. The ones on the bottom of the seats for your little crotch belt right there, those are the easy ones. The hard ones are the ones that are between the two people, because you really have to get in there at an odd angle and take it apart. Last times we've had to do this, it was like you had a crew of like 6 people working as best as they could. Operations was in there helping out. Everyone was doing it because the process takes a long time to do. This is your best case scenario. Scenario number 2, it's light. So you had an unloaded, not fully loaded gondola. I've had to do this once. A star, I'm sorry. I've had to do this, well, I've done this a couple times where the star only had like 6 people sitting in it. The park wasn't that busy, and it was stuck up at the top, or close to the top, about halfway. Now here's the sucky part. You remember how I was saying the counterweight is heavier than the star. Well, we're going to find out now just what that means, because we're going to say that the star is stuck halfway. There's only 6 people on it, which means the star is no longer heavier than the counterweight. The counterweight's heavier than the star. So now you have to get these 6 people off. How do you do that? Can you open your brakes up? Well, if you do, which is step number 1, the star goes up. So now you've got people that have been stuck on the ride, and they're stuck at, let's say, the 70-foot mark. Now you have to go in there and open up these brakes and actually send those people all the way to the very top of the ride. Why do you have to send those people to the top of the ride? Because I need the counterweight at the bottom of the ride. Sorry. So they have to get them all the way up there. Once the counterweight comes down to the bottom, I'm actually going to set the counterweight on its shocks down there. I'm going to go up and I'm going to use 2 jacks underneath the counterweight, support them underneath the counterweight, and then put some pressure up on that. About 2/3 of the way down the counterweight, there's 2 giant pins sitting in there. I'm going to remove the R-clips off the other side, and I'm going to pull those pins out. That is what's referred to as splitting the counterweight. Once I do that, I let the counterweight down a little bit to ensure it's not hung up on the main weight. And then once it's separated and free, now the star is theoretically heavier and it can come back down. That's a good thing, but it might not be enough, because remember I said there was only 6 people on it. If there was 6 kids on it, not 6 adults on it, the counterweight is still heavier than the star. Oh my gosh. Okay, now get your hands warmed up, because we're going to use a steering wheel, and it's going to suck, I promise you. Alright, so on the back of the AC motor there's a collar that sits there, bolted flange collar. Inside the control room there's a giant metal, looks like a steering wheel, sitting there. At this point, you have to go in and take that steering wheel and mount it to the back side of the AC motor. And you now have to bolt it together, which the bolts don't have to be like torqued down super tight. It's not a big issue, but you have to put the bolts on there and get them all finger tight. And now you need 2 people, one person to hold the electric motor brake open, another person to pump up the hydraulic brake and get that brake open, and now you need a person or 2 to sit there and now turn that steering wheel, and you have to manually turn that and bring the star down. That's right, every rotation you do on that steering wheel is 1 rotation through the motor, which is the rotation through the gearbox. The gearbox is something like 30 to 1, and it needs like 300 rotations to bring the star all the way back down to the bottom. As you could probably tell, this is going to start to suck really quick. And it does. And you have to start rotating people because everyone's arms get tired as you're driving this thing down to the bottom. This is, oh, it's such a crappy thing. I wish it upon nobody. Oh my gosh, it sucks. The last evacuation is the star is up, out of position, it's up high, and you have experienced a catastrophic failure inside the winch assembly. Like, inside that big gearbox that's sitting in there, something has shattered and has come apart, and it is locked, mechanically bound internally, like you cannot move that thing anymore. There is one device that we have at the park. Every ride gets it. I've never used it before because it's detrimental to the ride, but it is called a cable pull or the cable tug that's supplied. Now, the way this works, this is a hydraulic power package unit. You bring this guy out and you put it onto these big mounting eyelets that's on the drum assembly, and then it goes up, and it's essentially a wedge that grabs the wire rope coming down, and you extend this hydraulic ram up the cable. It goes up, 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 and then you let it, and then you reverse the direction and pull that ram down, and as it comes down, it grabs the cable and then starts to pull the cable down. And you have to keep doing that. You keep raising the ram up, grabbing the cable, and pulling the cable down. You're literally using one cable, and you're dragging the entire assembly over that set of drums. Remember I said, like, oh, the drum, those ropes can slide on there because there's only the tension of the counterweight holding it. Well, you can grab that whole assembly and drag it down. Now, like I said, when you're done with this and you get your people off, the ride is down. It's down, down, down. Because obviously something has really messed up inside of your winch package, so that is really going to hold the ride down. But now you've destroyed one of those wire ropes, at least one of those wire ropes. And any reputable park would never open that ride back up after doing that and just replace the one wire rope. You would replace all 6 at a minimum. So you're talking lots of downtime on the ride. Now, one thing I forgot to cover earlier when I was talking about the lifting cables is where they go through on the star, they actually pass through the steel frame, and then underneath there they go through these big wound coil springs with a big clamp on the bottom of it that actually supports the wire rope. And what you have to do is you can tension those springs to put different tension on those cables. So when you replace all the cables, you go through and you get everything correct. You run the cable over through its assemblies, you put it back onto its counterweight, and you get them snugged up. And then what you start to do is you start to bring tension on everything. So initially, this is just done by feel. It's like, okay, all of these feel the same. And then you move the star a little bit up and down. Doesn't take much, just a couple feet up and down, up and down. Then you go back up there and you use a wire rope tensioner gauge. Now this thing, it looks like, a lot of them look like a triangle basically. It's 2 points and the third point is a strain between the two. So depending on how much strain that gauge encounters, it will tell you theoretically, by trying to move the cable that direction, it will tell you theoretically how much tension is on that cable. So you go through to each one of the cables and you hook it up and you say, okay, this one has 1,600 pounds of tension, the next one has 1,700 pounds of tension, the next one has 1,400 pounds of tension. So once you start writing all those down, you get yourself an idea and say, okay, this cable over here I need to loosen, this cable over here I need to tighten, and you go do those 2 adjustments real quick, and then all the numbers have shifted again. It takes a long time to set those numbers up correctly to where those cables are all within 50-ish pounds of each other, and then you got to run the ride a bunch up and down and let all the slack and everything that's in those cables coming up and back down to the counterweight and all that, they run more slack out of the system and they kind of break in a little bit, and then you have to redo those adjustments again. And I believe that's on the monthly, I think that's actually on a quarterly, to put the cable strain device on there and check the tension on the cables. These rides are more of a pain in the butt than I remember. All right, while we're back on the cable subject, we'll talk about cable slip. Because of that tension across the drum, if you over oil the cables, or if the drum gets really greasy hydraulic fluid on it and stuff like that, the cables can still slip on that. So what they actually do in the morning time is we'll run a brake cable check. So we'll run the star up the tower as fast as possible, because remember, the counterweight's heavier than the star is. So we'll run the star up, bringing the counterweight down towards gravity as fast as possible, and then we basically e-stop the ride. When we e-stop it, the motor package will stop, the drum will stop, and it's got an encoder on the drum that says how fast it was going. It stops. Everything in there stops to 0. Like in a heartbeat. Boom. Done. Well, the cables don't stop. The cables continue to slide over that drum as it's doing its job. So what you get is that up on top, there's a lot of encoders and tachometers up on top as well. So the ride starts basically a math problem. When you hit the e-stop, as soon as the drum stops turning, it starts counting what the encoders are doing up on top, and you get a delta between the two essentially. So as it's going up full speed, and I go, okay, and I hit the e-stop button, I get a value back. A lot of times it's like a meter, a couple feet basically, where the drum has stopped, but the ride continued to go a couple of feet. So this is cable slippage over the drum. That's one of the things that we check. Now the cables aren't supposed to be that oily and greasy. They're supposed to be pretty clean, but they do have to be serviced enough to where they don't rust. So it's a fine line to walk. Anytime you're dealing with lifting cables, it's a fine line to walk. If you take a wire rope class, the wire rope class will tell you to keep those things nice and oily and greasy unless they're being driven. And then they start this balance of like, you gotta kind of keep the right oil on them so it doesn't interfere with your lifting process. And skis, aerial lifts and stuff like that, they have a lot of problem with that because that whole assembly has to be driven on these things. So wire rope tension is a really big deal with lifts and things like that. All right, while we're on the subject of positions, let's talk about positions up and down the tower. There is realistically 2 areas that the ride really cares about. The first one is called its park position. So it goes up to its park position, which is actually, unlike a lift hill, the park position's just a little bit off the ground. It's about 15-20 feet off the ground right there. At the park position, it pretty much won't enable its rotation drives below that park position. This park position can be higher depending on the model. I've seen rides installed where it was like it had buildings and trees and stuff around it that were really high up. It did not enable its drive below that position. So my park position at my ride might be 15 feet off the ground, but the park position at one of these other rides might be 50 feet off the ground, just depending on the clearances that are around it. Wherever that park position is, you have to figure that the ride can do full RPM spinning at that lowest position. So when the swings come all the way out, like the Peter Griffin episode where the swings are swinging around on there,
Gonna be great! Yay!
when the swings come all the way out like that, you have to assume that the ride can stay right there and operate like that. So if there's anything too close in that area...
Oh, who kicked me?
Sorry!
What the hell?
My bad!
Ow, who's doing that?
It's that jerk!
Park position's too low. You need to keep it going up higher until it's cleared all of those elements. The other one is your stop position at the very, very top of the ride. The stop position has... It's got your main stop, and it's got your oh crap stop up there. So as it comes up to it, your main stop, this is where the ride won't go past. It says right here, I'm not going to go past this point. But then up above it, and it's not very far actually, it's only about a foot above that, is this oh crap position. And once that hits, it locks down everything. It locks the brakes, it locks the PLC up, it stops everything in the ride because it says it's up too high. Now, how do they record this and keep this with powering down, powering up? The ride doesn't have like a block system to remember where it is. So how do they do that? They use mechanical retained switches. So these are commonly referred to as cross switches, and they also use these 90-degree switches. The 90-degree ones are easiest to explain because I could use my fingers right here like this. But the cross is the exact same principle, just imagine it on 4 sides. We only use the one side. Honestly, you could pretty much use these 90-degree switches like this everywhere on the ride, but they didn't do it. All right, so here's what I do. On the side of my tower, I put a 90-degree switch on like this. And then on the star, I put a flag plate on down here. Now, as I raise the star up, it hits this switch, cross switch or 90-degree switch, and simply rotates it like that as it passes up. Now, if I kill the power, reset the PLC, do all that other stuff, and I turn the ride back on, the ride looks at the position of this switch and says, hey, the star is above me. And then it looks at the next switch above it, and it might be in this position too. It says, hey, the star is above me. And then it looks at the third switch up the tower, and that switch is still sitting in this position. It says, star is not above me. So it's like, okay, so the ride instantly knows roughly where the star is. There is about 4 of these up the tower, so it kind of knows where it is. And then as the star passes back down, that flag plate comes back down, hits that switch, turns it back down. The thing that we had the most trouble with when it came to these switches was false readings, where they did not reset the position. So sometimes you would say this switch was going up, and it would go up a little bit like this, and then kind of slip, and then it would trigger and go right back down. Now, or the opposite, where it would come back down, and it would go like this, and go like that. Now, in the programming, they programmed in where these switches were in pulses on the encoder. So as the thing was turning, it would give it a value. And as it was going up, it would say, hey, this switch is 30 feet up the tower. So it's acceptable for this switch to change state around 28.5 feet or around 31.5 feet, somewhere in that window. But as soon as I go outside of that window on either side, and that's in the wrong state, fault. Stop the ride. We've lost track of where the star is. It's like, okay. So what happens is that I'm coming up, here I come up, 27, 28, 29, 30, 31, 32, click, fault. It just said 32. Why? Because my cross switch is pointing down, and it said I'm okay for the star to be either down below me or at most 31.5 up there. Yeah, what happened? It's like, well, I'm still pointing down, and the star now says it's at 32 up here. That's a problem. That's a position fault. So it's like, okay, these were particularly hard because sometimes you had to coax it into thinking that the star was somewhere where it wasn't. But a lot of times the easiest thing to do for that was the mechanic threw on a climbing harness real quick, scurried up the tower to wherever the switch was, and then changed the position of the switch to whatever it needed to be. So typically what we did is, like on the cross switches, we would put duct tape on the sides that weren't being used because we wouldn't use all 4 sections. We would only use one, right? So we put duct tape across there, and the mechanic would go up and see one where the open end of the pie was facing down, but the star was above it. So they go over to that one real quick, reach over there and just go like that, and they go, okay. They'd scurry back down, reset the ride, manual mode, bring the ride back down. That was a pretty common fix for those rides. Other one was just some communication faults and things like that. Lots of time you do the technical process of cycling the ON OFF switch, and it would fix a lot of that stuff and bring it back up. The last one is programming a cycle. Now, we had this really cool function where we got to program our own cycles in there. Now, we did it with engineering's help because there was still stuff that could go wrong. So we were able to come up with our own cycles of what we wanted to do. We said, the engineer showed me how to program a cycle, And it was pretty cool. I went into the computer and I was able to type in, okay, I want it to go to this position, spin to this RPM, wait till 60 seconds passed, and then do this. And then we would put that all in and go watch it and come back to the PLC and make adjustments. Now, remember, PLCs are strictly hands-off, but we were doing this before we did a major modification to the ride. So the state hadn't inspected it yet. The ride was closed down to the general public. Nobody was going on this thing. So we were just in there setting cycles because it was just us running it. So it was pretty cool. And then the last thing was the way the program worked. I can't remember the exact function that's in there, but basically once it was set to where we did it, we put it back down and we had to manually toggle this bit in the program. I don't remember what it was, but that started a recording inside the program. And I can't tell you the specifics of how it worked because I wasn't that familiar with this particular process, but I remember we got it back into automatic mode. We went down, we had the program selected, and then we hit the toggle on that bit and it started recording, and then we ran the cycle like it was supposed to do, and it came back down. And then at the end of that process, we toggled that bit again, and now that was officially it was like program number 7 or something like that. We got a cool one to run for like the fright time of year. We ran it backwards. So that was a fun one too. That was not an unusual thing for the Funtime version. Theirs at the start didn't know if the ride was running forward or backwards. It counted speed, but it didn't know which direction it was going. But every once in a while, the drive would say, oh, go backwards, and then the drive would actually register backwards and the ride would fault out. But it wasn't anything more than like the ride just started to turn backwards just a hair and then would shut off. But we did program a full backward cycle for our fright time of year. All right, I think that's going to do it for this video. Like, subscribe, share, do all that stuff downstairs. It does help me out, and I do appreciate it. If you want to contact me, you could always do it in the comments down below. Email me. You could email me at ryan@yahoo.com. You have any fun stories to add to it? I mean, there's a lot of Star Flyers out there. I'm assuming there's a lot of Star Flyer stories. You ever seen anybody get sick on one of these things when they're high up in the air? That's not a good thing. All right. I'm Ryan the Ryan Mechanic. Stay off the air gates. Bye.